we will now develop a technique for measuring the area obtained by revolving this curve about an axis. If you revolve this curve about an axis, you generate an area. And how do you obtain the area of such revolution? Well, let's consider a curve PQ drawn here, just like in the earlier case, from x equal to A to x equal to B. Well, the length of that curve is from P to Q. Now, if this curve is revolved about the x-axis, can you visualize the shape of the surface generated? Now, if this curve is revolved about the x-axis, it is going to generate a beautiful surface. Can you visualize what that surface look like? Well, if you want to visualize, what we can do is we can take a point on the curve. If you take a point on the curve and revolve it about the x-axis, what you will generate is a circle. Is that right? That's right. So any point on this curve, if you revolve it about the x-axis, it will generate a circle. That means infinite number of points on the curve, when revolved about the x-axis, will generate infinite number of circles. And the surface that is generated by the curve is actually defined by these infinite number of circles. Each point on the curve revolves about the x-axis, generating a circle. Can you visualize that in your mind? If I have a curve like this, and if I want to revolve it about the x-axis, now that is the x-axis, I take a point on the curve and revolve it about the x-axis, it will generate a circle. Any point on the curve revolved about the x-axis will generate a circle. That means the whole surface generated by revolving this curve is actually defined by these infinite number of circles. I hope you understand that visualization. Alright, now that means if you can reflect the PQ on the x-axis, you will get this. Is that right? Alright, I hope you can see that. Now, if you take the point Q and revolve it about the x-axis, this is the circle you generate. Now, another point revolved about the x-axis, you generate that circle. At another point revolved about the x-axis, you generate at another circle. And so on. You can actually take infinite number of points and revolve them about the x-axis, generating circles. That means these circles are actually generating that whole surface. Can you visualize what the whole surface look like? Now, what is the radius of each of this circle? What is the radius of, let's say, this third circle. What is the radius? The radius is that distance. And that distance is the distance of the curve from the x-axis. And the distance of the graph of a curve from the x-axis is the function value, y equal to. So if this is the graph of y equal to f of x, then the radius equal to f of x. That's right. So each of these radii actually give you the function value. If this is the graph of y equal to x squared, then each of these radii will be y equal to x squared. In other words, this will be x squared, this will be x squared, this will be x squared. Of course, each of these will be different because each x value is different. Now, tell me, what is the shape of the surface generated when the graph of y equal to x squared is revolved about the y-axis. Now, I have the graph of y equal to x squared in here, and if you revolve it about the x-axis, how does the shape generated look like? Can you visualize? Now this x-axis, this y-axis shifting slightly up is not an error. I did that deliberately so that I can now draw these circles that generate the surface that is generated when y equal to x squared is revolved about the y-axis. So this is the graph of y equal to x squared. If you take points on this graph and revolve it about the y-axis, you will generate infinite number of circles. And how will the total surface look like? Now, have you got any idea? Now look at this beautiful picture that will be generated by doing so. Each point revolved about the x-axis generate these circles. So each of these circles actually define the surface that is created as a result of revolving that arc. So that beautiful surface is generated by revolving the graph of y equal to x squared about the y-axis. Now watch the circles that are generated by revolving each point. Now here, only some circles are shown. There are actually infinite number of circles that will generate this beautiful surface. Okay, now what is the radius of each circle? What is the radius of each circle? In the diagram above here, the radius of each circle is f of x, y equal to f of x. Now, what is the radius here? The distance measured from the y-axis. The radius of this circle is this, which is the distance of the function graph from the y-axis, which is called x equal to. Is that right? That means you need to write the function as a function of y. Y equal to x squared is the same as x equal to square root of y. So the radius of each of the circle is x equal to square root of y. Again, let's go to the upper diagram. In the upper diagram, the radius of each of the circle is y equal to x squared. The radius of each of the circles in the lower diagram is x equal to square root of y. I hope you understand that concept. Okay, look at some typical surfaces when familiar curves are revolved. Now, look at this. This is a curve. Can you give me an equation for this? Well, this can be something like y equal to, see, y equal to negative x is this, negative x plus something, negative x plus 2, negative x plus 3 will give you that line. If you revolve that line about the y-axis, look at the beautiful cone that is generated. If you take each point on this and revolve it about the y-axis, you generate these circles. And you can see all these circles finally generate that surface. And look at this. You have a semicircle, and what happens when this is revolved about the y-axis? Now visualize this in your mind. Take points on the curve and revolve to generate these circles. And look at that beautiful solid generated. And when you have a different kind of, well, this is bulging more towards the right. Now this is more flat, and look at the shape of the solid. And this is called a conical frustum, and that is generated by revolving this line about the y-axis. That leaves that hole at the top. And look at how a cylinder is generated. A cylinder is generated by revolving a vertical line about the y-axis. generating that cylinder. And finally a zone, a curve like this, revolved about the y-axis. So most of the solids that you see around, the surfaces, these are not solids, we are only generating the surfaces. So most of the surfaces that you see around are actually generated by revolving appropriate functions either about the x-axis or y-axis or any other convenient axis. Alright, look at another one. Now, I want you to watch how that surface is generated. Now, and these are the various circles. And how does those various circles, the thousands of these circles, generate that beautiful surface? Alright? Look at it one more time. It is the curve. It is that curve that is, remember, it is not generating a solid. It is generating just a surface. Alright. Now how about this? That's again generating a surface. Now tell me, how is this surface generated? If you have a line like this and revolve it about an appropriate axis, I want you to visualize what axis is used to generate this surface. And finally, look at one more. If you revolve this curve about the y-axis, I want you to check in your mind. You take each point on this curve and revolve it about the y-axis. You generate this beautiful surface. Alright, now that gives you an appreciation of how beautiful the method of calculus is to interpret the beautiful world that we see around here. Is that right? Okay, let's now develop a method of measuring this area. How do we calculate the area of revolution? That's our concern now. Now, take a small part of the curve of length ds. Now, if you take a small part of length ds here, that is very small, almost like a point, because only when the length of that ds is very small will it be equal to a straight line. And the length of such a small arc is given by ds equal to square root of 1 plus dy by dx all squared dx. That is the length of the arc. So if you take a small length of the arc ds, that will be its length. And if you revolve such, suppose this is the ds. This is the ds, which is very small. Tell me, if you revolve this about the x-axis, what are you actually generating? Well, if you revolve just a point, you generate a circle. If you revolve a line of length ds, you are actually generating the surface of a disc-like structure. Is that right? That's right. You're actually generating the surface of a disc. Not the whole disc, because the inside is hollow. The surface of a disc. That is what you generate by revolving that ds around the x-axis. So revolving ds around the x-axis, you generate a cylindrical surface, because the cylindrical surface inside is actually hollow. So this is what actually you generate. You see, if that is ds, if you revolve this about the x-axis, what you generate will be a surface like this. Now, what is the area of this cylinder? How do you find the area of the cylinder? The area of the cylinder is, if you look here, this is a circle. The circumference of this circle is 2 pi r, and that circumference multiplied by this length will give you the area. So 2 pi r multiplied by that length will give you the area. Now here, radius. What is the radius? If you look here, the radius of that ds is this length, which is f of x. And the thickness of the cylinder is ds. So if the radius is r of x, a function of x, so 2 pi r of x is the circumference multiplied by ds, and ds is this, will give you the area of this cylindrical surface. Now, that is created by revolving this ds, and there are hundreds of such ds you can revolve, generating cylindrical surfaces. Add all those surface areas, you will get the complete area generated by revolving this curve. And that's the method. Adding all those areas means integrate. So once again, revolving ds about the x-axis generates a cylinder of radius r of x. The radius r of x is that distance, which is the function itself, r of x equal to f of x. So the radius of each of the cylinder is f of x. Okay, the surface area of this cylinder is, you remember how we got the surface area? The surface area will be the circumference multiplied by ds. Will be 2 pi r of x is the circumference multiplied by ds will give you the area of such a surface. Now, therefore, dA will be 2 pi r of x times ds. ds is the length of the arc, and the length of the arc is this quantity. So that will be 2 pi r of x square root 1 plus dy by dx all squared dx. So in finding the area of the surface of revolution, the first thing we need to do is to find the arc length. Is that right? And of course, then the radius of revolution. And once you have dA, what all we need to do is integrate that dA from x equal to a to x equal to b. And therefore the total area is integral a to b 2 pi r of x times ds. ds is square root 1 plus quantity dy by dx squared dx. Alright. If the graph of f of x is revolved about a vertical axis, you see the equation we developed so far is revolving the area about a horizontal axis. What happens if you revolve it about a vertical axis? What kind of area you get? That will be 2 pi integral a to b r of x square root f prime x squared dx. So one thing you need to take care here, if the axis of revolution is horizontal, then the radius is a function of x, and the arc length will also involve functions of x. If the axis of revolution is vertical, then the radius, remember the radius will be measured from the axis, will be a function of y, and the arc length, the ds, will also involve functions of y. Now, that's very important to know. So, if the axis of revolution is horizontal, the area of revolution is 2 pi integral a to b r of x square root 1 plus f prime x squared dx. And if the axis of revolution is vertical, a equal to 2 pi integral c to d. Let's not call it a to b. C to d r of y square root 1 plus f prime y squared dx. Let's do a problem using this. set up and evaluate a definite integral for the area of the surface generated by revolving the graph of y equal to square root of x about the x-axis on the interval 1 to 4. Alright, first of all, draw that figure and see how that curve looked like. Y equals square root of x is something like this. And you need to revolve it about the x-axis. And this is the equation for the area of the surface generated by revolving a surface about a horizontal axis. Now, what are the information you need? Starting from here, we have f of x. This is y equal to square root x is f of x. We need to find f prime x. We need to square it. Then we need to add 1 to it. We need to take the square root of it. Now, that is that quantity. Then the radius of revolution. The radius of revolution in this case will be y equal to square root of x. Alright, where do we start? We start with f of x equal to square root of x. What is the derivative of that? F prime x. The derivative of square root of x is 1 over 2 square root of x. Is that right? But you can also do it by using the power rule. Square root of x means x to the power 1/2. Or, I have told you from the beginning, learn this as a result that you need to know. The derivative of square root of u is 1 over square root u times u prime. The derivative of square root x is 1 over 2 square root x. So we've found f prime x. Now we square it. So what is f prime of x squared? Is 1 over 4x. Now you need to add a 1 to it. So what is 1 plus f prime x all squared? That is 1 plus 1 over 4x. Simplify it. That will be 4x plus 1 over 4x. We now need to take the square root of it. So square root of that will be square root of 4x plus 1 over 4x. And look at the way I simplified it. That will be, we split this into two square root quantities. Square root 4x plus 1 over square root 4x. Square root 4x is 2 square root of x. So that simplifies as 1 over 2 square root x times square root 4x plus 1. Now that is this quantity. Now what is r of x? The radius of revolution r of x equal to f of x, which is square root of x. So that is our f of x equal to square root of x, and the radius of revolution will be, when you revolve, that radius will be f of x. That's right. R of x equal to f of x. There you go. And therefore, let's bring it all together. The area of revolution is 2 pi integral a to b, which is given to us, 0 to 4. R of x is square root of x. And this quantity is simplified like this. So let's put it all together. That would be 2 pi integral 1 to 4. 1 over 2 square root x, well, r of x is square root of x, times this quantity. And you can see square root x and square root x will cancel, and the 2 and that 2 will cancel, leaving us pi integral 1 to 4 of 4x plus 1 and the square root dx. Now, can you do this integration on your own? What's the method? Well, the method is substitute the quantity 4x plus 1 equal to u, and when this becomes u, you need to replace your dx. What's the method? Take the differential of both sides. Differential of 4x is 4 dx. Differential of 1 is 0. and differential of u is u. 4 dx equal to du, therefore dx equal to du divided by 4. And so when this quantity is replaced by u, dx will be du over 4. What else do we need to do before we write down? We need to change the limits using this substitution. When x equal to 1, that's our lower limit. When x equal to 1, this will be 4 plus 1, 5. U will be equal to 5. When x equal to 4, that will be 4 times 4, 16 plus 1. U will be 17. So change the limits. When x equal to 1, u equal to 5. When x equal to 4, u equal to 17. Just put those values of x in our substitution and find the value of u. So what is the area now equal to? Area is now pi times integral u changes from 5 to 17 square root of u times dx is du over 4. And now this 4 comes out, this will become pi divided by 4. So pi over 4 integral 5 to 17 u to the power of 1/2 du. You know how to integrate u to the power of 1/2 du. What is that? U to the power of 1/2 plus 1 over 1/2 plus 1, which is u to the power of 3 over 2 over 3 over 2. So pi over 4, u to the power of 3 over 2 over 3 over 2, from u equal to 5 to u equal to 17. Now, look at the way we can simplify this. 3 divided by 2, that 2 will go up. That 2 will cancel with the 4, leaving a 2 outside. So that will be pi over 2. And I can also take that 3 outside. Is that right? And the 2 and the 3 will multiply to give me pi over 6. Did you understand that? 3 divided by 2. The 2 goes up. And the 3 multiplies by 4. That will be 2 over 12, or that will be pi over 6. That will be pi over 6, u to the power of 3 over 2, from u equal to 5 to 17. What we need to now do is replace u by 17 minus replace u by 5. That will be pi over 6, 17 to the power of 3 over 2, minus 5 to the power of 3 over 2. There's no way we can simplify this. The only thing we can do is put that in the calculator and get an approximate value. So that approximately is 30.85 square unit. So when this arc is revolved about the x-axis, the surface generated has an area of 30.85 square unit. Can you visualize what that area will look like? All right. You can also do this on the calculator, just like I showed you. Find out integral and follow the keystrokes I just showed you, and it gives you 30.85. All right, let's do another one. Find the approximate surface area, which obviously suggests that you will not be able to integrate it, to simplify it fully to get the exact value. You got to find the approximate value. That means use your calculator to evaluate the integral of the surface generated when the graph of y equal to ln x is revolved about the x-axis. Do you remember how the graph of y equal to ln x looked like? Like that. And if you revolve it about the y-axis, it's going to be like that. A graph like this, revolved about the y-axis, you produce a beautiful flower vase-like structure. All right, that's our equation. Carry that with you. So our function is y equal to ln x. Well, we start by finding the derivative of that. What is the derivative of ln x? If f of x equal to ln x, what is f prime x? Is 1 over x. Our next task is to find the square of that. So f prime x, the quantity squared, is 1 over x squared. Well, we found f prime x squared. We need to add 1 to that. 1 plus f prime x squared is 1 plus 1 over x squared. Let's simplify this. That will be x squared plus 1 over x squared. What is the next step? We need to find the square root of this quantity. Is that right? This quantity needs to be under square root. So find the square root of 1 plus f prime x squared is square root of x squared plus 1 over x. Well, you can again split this into 2 square root. That will be square root x squared plus 1 on the numerator, and square root x squared is x on the denominator. So that will be 1 over x square root x squared plus 1. That is this quantity. And what is r of x? Now this is the graph of y equal to ln x. And you're going to revolve it about the y-axis. Now look at the surfaces that are generated. This is the radius. Now what is that radius? The radius is the distance measured from the axis to any point on the graph, and that distance is called x. So r of x equal to x. That's right. So this r of x is actually x. R of x equal to x. Now therefore we have now the complete formula for the area. A equal to 2 pi integral a to b. We know the values of a and b. R of x equal to x, and the square root quantity equal to this. Replace all that. It will be 2 pi integral 1 to e x times 1 over x square root x squared plus 1 dx. And that will be 2 pi integral 1 to e square root x squared plus 1 dx. Well, we haven't actually developed a method to integrate this yet, but soon we will know how to integrate quantities like this. So until then, we are going to find the value of this on the calculator. So go like this: 2 pi times finite integral square root x squared plus 1 when x goes from 1 to e. Alright, follow these keystrokes, and that will give you 22.9 is the approximate area of that surface generated. I hope you can visualize how this surface looks like when this curve is revolved about the y-axis.